Swayam Prabha. Digital India. Educated India.
Welcome to lecture 34 of the course on multivariate data mining, methods and applications. In the last lecture, we have discussed the basics of decision trees. Of course, before using a decision tree, it requires training. You have a learning set, and on the basis of learning set, you want to train the decision tree. And while training the decision tree, you have to take several decisions like which feature variable you have to use at a particular node, then what kind of split you form on the basis of that particular feature variable, and definitely you also require certain criterion on the basis of you split a particular node. Then sometimes the tree is overgrown and overfitted, and you may be interested in reducing the size of the tree. Then you use the process of pruning the tree. You put some penalty to size of the tree for the pruning purpose, and then you, in some sense, you can say that you cut down the branches which are not so important for you, or you cut down the capital T denotes T equal to tau 1, tau 2, tau terminal nodes for T. The true misclassification is the misclassification rate for the entire tree. So you consider all the terminal nodes, say L equal to 1 to capital L. Then suppose capital R tau L is the misclassification rate for the terminal node tau L. So you take R tau L here. Then P tau L is the probability that observation is at node tau L. So you multiply R tau L by P tau L, and then you add over all terminal nodes. So this gives you the true misclassification rate. Then you have to estimate R tau L and P tau L. So we estimate R tau L by small r tau L and capital P tau L by small p tau L, where the small p tau L is the proportion of all observations at node tau L. And then using the estimates of R tau L and P tau L, we can estimate RT. So we estimate RT by R hat T equal to summation L equal to 1 to capital L. You are estimating capital R tau L by small r tau L and capital P tau L by small p tau L, and then you write it equal to summation over L R hat tau L, where R hat tau L is equal to small r tau L into p tau L. Now there is a shortcoming of R T or R head T. R head T actually always decreases as tree grows. So R head T dash is always less than or equal to R head T if T dash is formed by splitting terminal nodes of T. Further, R head T is 0 if each terminal node has only a single observation. So, according to R head T, the best possibility is that each terminal node has only a single observation. But if you have just a single observation on each terminal node, obviously it is not going to serve your purpose. So, in that way, R head T is not good. Further, R head T does not take into account the complexity of the tree, and it may lead to overfitting. Now, what we mean by overfitting? A decision tree T overfits the training data if there exists any other tree set T dash such that T has smaller error than T dash on the training set, but T has larger error than T dash on the test set. Now, this is interesting. On the training set, T performs better than T dash. But when we use the test set, then on the test set, T dash is performing better than T. So, T has larger error. What does it mean? It means that your training set is not a proper sample or proper representative of the entire data set. Ultimately, how we select training set? We consider the entire data set and then we select a random sample as training set. So, it is not a proper representative of your entire data set, and ultimately you want a decision tree which works well for the entire data set. So, this is the problem of overfitting. And then why we get overfitting? Too much noise in the training data. And if there is too much noise in the training data, it means the data is not a representative sample. And if it is not a true representative, a proper representative sample, then it may lead to a split on irrelevant features. Or another possibility is too much variance in the training data, which may lead to incorrect class labels. Now, to control the overfitting, one may employ pruning the tree. And the process of pruning the tree involves removing leaves and assign the majority label of the parent to all items. So, we remove the leaves. Further, there are two possibilities: tree pruning. Say we grow the tree. In pre-pruning, we stop growing the tree at some point when there is insufficient data to make reliable decisions. So, if a particular node gets insufficient data, it has too small size of sample, a particular node. Then we stop growing the tree at that particular node. So we do no further splitting. Post pruning. In post pruning, we grow the full decision tree. And then after growing the full decision tree, we remove nodes for which we have insufficient evidence. So first what we do? We grow the full tree. Obviously it is too big, and then we start pruning by removing the nodes for which you don't have sufficient evidence, the nodes which are not so important or which are not playing any crucial role. Now we consider cost complexity pruning measure. So suppose alpha is the complexity parameter which is greater than or equal to 0, and for tau belonging to t, we set r alpha tau equal to r hat tau plus alpha. Now suppose capital L is the length of t, then we are having a penalty for the complexity. This L actually denotes the complexity of the tree. So we must put some penalty to capital L. Then the cost complexity pruning measure is defined as, say, R alpha t equal to, now we consider all the terminal nodes. We take summation over L from 1 to capital L, R alpha tau alpha. And if we add this over all the terminal nodes, then we obtain R hat t here. R hat t is equal to summation over L, R hat tau L plus alpha times L. So this is the penalty part. Now, how to choose the best split? A measure of goodness of a split is node impurity function. Say I tau is equal to 5 P1 given tau, P2 given tau, so on Pk given tau, where Pk given tau is estimate of the probability that x belongs to pi k given tau, and x belongs to pi k given tau denotes x is in pi k given that it falls into node tau. So this is the probability that x is in pi k provided or given that it falls into the node tau. Then entropy function is, say, I tau is equal to minus summation k equal to 1 to capital K, p k given tau log p k given tau. For a particular node, we know that the entropy function is pk given tau log pk given tau, and then we are taking the summation over k equal to 1 to capital K. We are taking summation over all the classes. Gini divergence index is another measure of impurity, so one can use Gini divergence index also. Then best split is that for which measure of goodness of a split. You take any measure of goodness of a split. Then the best split, this measure of goodness of a split is maximum, or measure of impurity is minimum. Now here is the pruning algorithm. we grow the tree large, say up to T maximum, where we continue splitting until each node contains less than, say, n minimum observations. Otherwise, it may lead to a tree having just a single observation in each node. So, we fix n minimum, which is the minimum number of observations in each node. Then compute an estimate of misclassification rate, or tau, for every node tau belonging to T maximum. So, we consider each and every node tau and we compute or we obtain the estimate of misclassification rate for each node. Then we prune the tree upwards towards its root nodes, so that at each stage of pruning, the estimate of RT is minimized, and we use cost complexity pruning measure R alpha T as an estimate of RT. So, we consider this cost complexity pruning measure R alpha T as an estimator of RT. Now, we adopt a regularization approach for tree pruning. Say alpha is the cost complexity parameter, and then for node tau belonging to T, we set R alpha tau equal to, say, R E tau plus alpha for a particular node. Cost complexity pruning measure for the tree is defined as R alpha tau is equal to summation L equal to 1 to capital L R E tau, which is equal to R E T plus alpha, the length of the tree. Here, this mod T curled is equal to L, and this denotes the number of terminal nodes in subtree T of T maximum. T is a subtree of T maximum, and mod T curl denotes the number of terminal nodes in this subtree. Then alpha mod T curl is the penalty term for tree size, and for given alpha, we choose subtree T alpha of T maximum that minimizes R alpha T. Then the resulting tree is a minimizing or optimally pruned subtree of T maximum. For the given value of alpha, you can obtain the optimally pruned subtree of T maximum in this way. Now, there may be more than one minimizing subtree of T maximum. So, suppose you start from alpha equal to 0. Obviously, for alpha equal to 0, the minimizing tree is T maximum. And then we keep on increasing the value of alpha, say. Say, as alpha increases, terminal nodes of minimizing subtree decrease. And then, if alpha is very large, T maximum is completely pruned, and we are left with root node. So, for alpha equal to 0, we have minimizing tree as T maximum, and we keep on increasing the value of alpha. So, tree size gradually decreases, and ultimately, for a very large value of alpha, we reach to a position where the T maximum is completely pruned and we have just root node. So these are the two extremes, T maximum and just the root node. And in between somewhere you have to stop. Now suppose you have more than one minimizing subtrees. Then you can choose a tree with minimum terminal nodes. Now just I am stating this result without proof. There always exists a unique smallest minimizing subtree. And your problem is how to find this smallest minimizing subtree. Suppose alpha belongs to interval 0 to infinity. Obviously, for alpha equal to 0, it leads to T maximum. Further, the number of subtrees of T is finite. Then we keep on increasing the value of alpha. And suppose for alpha equal to alpha 1, the minimizing subtree is T1. Up to alpha less than alpha 1, the minimizing subtree is T maximum. But at alpha equal to alpha 1, the minimizing subtree becomes T1. Then T1 remains minimizing subtree until a point alpha equal to alpha 2. And once we reach alpha equal to alpha 2, a tree T2 equal to T alpha 2 becomes minimizing subtree. And then proceeding in this manner, we get an increasing sequence of complexity parameters, say alpha 1, alpha 2, so on, alpha m, and a finite sequence of subtrees of T maximum, say T maximum which is equal to T naught. And then we have a subtree of T maximum, say T1, and then we have a subtree T2 of both T1 and T naught, and so on, and ultimately we get Tm for alpha equal to alpha m. Then to reach from T maximum to T1, suppose tau belongs to T maximum and tau has daughter terminal nodes tau L and tau R. Then Re tau, the resubstitution estimate at terminal node tau, is greater than or equal to Re tau L plus Re tau R. And if the equality holds here, then prune the terminal nodes tau L and tau R. So in case of equality, we prune these two terminal nodes from the tree. And we continue pruning until no further pruning is possible. Then the resulting tree is T1. Then to reach from T1 to T2, we proceed in a similar manner. Say for any terminal node tau belonging to T1, let T tau be the subtree from root node tau. And T curl tau is equal to T1 dash, T2 dash, on TL tau dash. This is the set of terminal nodes of T tau. Further, suppose Re T tau is equal to summation over tau dash belonging to T curl tau, R E tau dash is equal to summation over L dash equal to 1 to L tau, R E tau dash L dash. Then R E tau is greater than R E T tau. And suppose R alpha T tau is equal to R E T tau plus alpha, the length of T curl tau. Further, as long as R alpha tau is greater than R alpha T tau, the subtree T tau has a smaller cost complexity than its root node tau, and we retain, in that case we retain T tau. The logic behind it is that as long as R alpha tau is greater than R alpha T tau, that is, the subtree T tau has a smaller cost complexity than its root node, it is worth going for the split. The subtrees or incorporating the subtrees is providing an improvement. So that's why we retain T tau. Now our next objective is to find the value of alpha. So now we consider the equations 1 and 5. Then we subtract 1 from 5. So what we get? R alpha T tau minus R alpha tau equal to R E T tau minus R E tau plus alpha mod T curl tau minus 1. Then we use the condition that R alpha tau is greater than R alpha T tau, and using this condition you easily observe that alpha is less than R E tau minus R E T tau divided by mod T curl tau minus 1. Actually, this quantity is less than 0. So, alpha T curl alpha minus 1, this quantity is less than R E tau. You take these two terms towards the left hand side, minus R E T tau, and then we get this inequality. Now the right hand side is reduction in R E due to moving from a single node to the subtree that node as root. So basically what we do in splitting, we are splitting the node tau into two subtrees, and then this quantity gives you the reduction in R E due to this kind of splitting, that is moving from a single node to the two subtrees. with that particular node as root. Then for tau belonging to T1, we define G1 tau equal to RRE tau minus RRE T1 tau divided by T curl 1 tau mod of this minus 1. In fact, here T1 tau is same as T tau. Just to distinguish between T1, T2, so on, we have taken this subscript 1 here. So we write G1 tau equal to this for tau not belonging to T curl alpha 1. Now, if G1 tau is greater than alpha 1, then you don't prune the non-terminal node tau belonging to T1. So, this quantity is G1 tau. And as long as G1 tau is greater than alpha 1, you just replace this alpha by alpha 1, then we don't prune for alpha equal to alpha 1. So, basically this G1 tau works as a critical value for alpha. Now, at each stage, we drop that node which has weakest link. Weakest link node tau 1 curl is the node of T1 tau which satisfies, say, G1 tau 1 curl equal to minimum tau belonging to T1 tau G1 tau. So, the node tau 1 curl belonging to T1 tau for which G1 tau is minimum for all tau belonging to T1 tau is the weakest link node. And we drop that node or we prune that node. Further, as alpha increases, tau 1 curl is the first node for which R alpha tau equal to R alpha T tau. And then we set alpha 2 equal to G1 tau 1 curl. And we define the subtree T2 equal to T alpha 2 of T1. So, we start from T1 and then we increase the value of alpha, and then this is the weakest link. So, as we increase the value of alpha, tau 1 curl is the first node for which R alpha tau is equal to R alpha T tau, and this is the first node which we are going to drop as we increase alpha. And then we set alpha 2 equal to G1 tau 1 curl, because at alpha 2 we are going to drop this particular node, and alpha 2 is equal to G1 tau 1 curl. As long as alpha goes beyond G1 tau 1 curl, we drop this tau 1 curl. And then the defined subtree is T2. T2 is a subtree of T1. And then we proceed further. In a similar manner, we keep on increasing the value of alpha. Using this approach, we find the weakest link, increase the value of alpha further, then that particular weakest link is the first link to be dropped, find the corresponding value of alpha, and then the subtree corresponding to that particular value of alpha, and so on. So, we get the trees T2, T3 and so on. Then, how to choose a tree in case of several minimizing subtrees? at a particular stage, you may face this problem. You may have several minimizing subtrees. So, suppose T alpha is the smallest minimizing subtree if it is a minimizing subtree and R alpha T equal to R alpha T alpha. And then T alpha is a subtree of T. Now we get a finite increasing sequence of complexity parameters, say 0 equal to alpha naught, which is less than alpha 1, less than alpha 2, and so on, less than alpha m. And then we also get corresponding finite sequence of subtrees of T maximum. Say we write T naught equal to T maximum, and T1 is a subtree of T naught, T2 is a subtree of T1, and so on, Tn. We obtain T1 corresponding to alpha equal to alpha 1, we obtain T2 corresponding to alpha equal to alpha 2, and so on. We obtain Tm corresponding to alpha equal to alpha m. And as long as alpha belongs to alpha k plus 1, this semi-closed interval, Tk equal to T alpha k is the unique minimizing subtree. Choosing the best pruned subtree. Now you have a sequence of subtrees, and then the problem is which subtree of the sequence do we choose as the best pruned subtree. We obtain all the subtrees after pruning. Then ultimately you have to decide at which stage you should stop. For the large data set, we divide the observations into training set and test set. And then using the test set, we select the best pruned subtree. Then for the small data sets, we prefer cross-validation. So one can make use of cross-validation for selecting the best pruned subtree. So we consider independent test set. So what we do, we randomly assign the observations in the data set into a learning set and a test set. So suppose D is the data set. Then we have divided the data set into learning set L and the test set. So obviously D is equal to L union tau, and the intersection of these two sets, the learning set and the test set, is null set. So these two sets are disjoint. Now suppose Nt is the number of observations in the test set, and observations in L and T are drawn independently from the same distribution. Then first we grow the tree T maximum from L. We consider the learning set and then we grow the tree up to T maximum. And then we prune it from the bottom up to give the sequence of subtrees, say T1, T2, so on, Tm. And actually all these trees assign a class to each terminal node. Now we take each of Nt test set observations. So now you have to select one of these subtrees on the basis of test set observations. So we take the test set observations. In all you have Nt test set observations. We drop down the test set observations to the subtree Tk. So suppose you select one of these subtrees, Tk. So we drop down the test set observations to this subtree and classify into one of the different classes. And since you also know the class of each observation of the test set, so you can easily check whether the observation is correctly classified or not. Then we estimate RTK by say RTSTK, which is the resubstitution estimate computed using the independent test set. This TS denotes the test set. That is RTS TK is equal to R hat TK. Now, if the costs of misclassification are same for each class, say RTS TK is proportional to number of test set observations misclassified by Tk. Then the best pruned subtree T star is selected as RTS T star equal to minimum over K RTS Tk. So we select that subtree which minimizes RTSTK over K, and RTSTK is the misclassification rate of the best pruned tree. Now we consider the estimation of standard error of RTST, the best pruned subtree. Now suppose P star, which is equal to RT, is the probability that an observation of the test set drop down a tree T is misclassified. Then the probability distribution of number of misclassified observations is a binomial distribution with parameters anti P star, and P equal to RTST is the proportion of misclassified observations in T. Then expectation of P is equal to say NT times P. This follows a binomial distribution B NT P star. So expectation of NT P is equal to NT P star, and variance of NT P is equal to NT P star 1 minus P star. So from here we observe that expectation of P is equal to P star and variance of P is equal to P star 1 minus P star upon NT. Then an estimator of standard error of RTST, which we denote by SE hat RTST, is equal to RTST 1 minus RTST divided by NT to the power half. This is the variance, and then obviously if we take a square root of this, we get the standard deviation of P. Then in the expression for standard deviation, we replace P star by its estimator, which is RTST. So you get this estimator of the standard error of RTST. Now we come to the cross validation. Say we consider V-fold cross validation. In V-fold cross validation, we randomly divide the data set D into V, say usually we take V equal to 5 or 10 equally sized disjoint subsets, and then D is equal to union over V dV, and dV intersection dV dash is equal to 5, because all these subsets dV are disjoint. Then we create V different learning sets and test sets as, say, LV equal to D minus TV and TV equal to DV for all V equal to 1 to capital V. So we get these capital V learning sets and test sets. Then grow the Vth auxiliary tree, and then we obtain T maximum V on the basis of Vth learning set, and this we do for all V. For given complexity parameter alpha, TV alpha is the best pruned subtree of TV maximum. So this is the best pruned subtree based on the Vth sample or Vth learning set, LV. Then drop each observation in the Vth test set down the tree TV alpha for V equal to 1 to capital V. And suppose Nij V alpha is the number of jth class observations in TV that are classified as being from the ith class for all j equal to 1 to k, V equal to 1 to V. And Nij alpha is the number of jth class observations that are misclassified as from the ith class. Then Nj is the number of observations in D that belong to the jth class. Now D is equal to union TV and TVs are disjoint. So Nij alpha is equal to summation over V Nij V alpha for all I and j. And suppose misclassification costs are equal for all classes, then T alpha is the minimizing subtree of T maximum, and the estimated misclassification rate over D is, say, R CVV T alpha equal to 1 upon n summation over I summation over j Nij alpha. So this is the estimated misclassification rate over the entire data set using the cross validation. And suppose alpha k plus 1, this interval be the interval in which T alpha equal to Tk. Then for obtaining right sized subtree, we consider alpha k dash, which is the geometric mean of alpha k plus 1, and then we set R CVV Tk equal to R CVV T alpha k dash. So we choose this geometric mean of alpha k plus 1, and then we use this geometric mean here. And then we select best from subtree T star using the rule R CV T star equal to minimum over k R CV given V Tk, where R CV given V T star is the estimated misclassification rate. So we use this strategy in cross validation, V-fold cross validation for selecting the best pruned subtree. Now we consider one SE rule to overcome the instability in selecting the best pruned subtree. Now RT star, which is the minimum over K, RTK is the estimated misclassification rate, and for the test set, RT star is equal to RTST star. So we calculate RTST star from the test set, or for cross validation, we calculate RT star by RCV given V T star. We have already defined these quantities earlier. Then we choose a smallest tree T double star that satisfies one SE rule, that is R head T double star is less than or equal to R head T star plus standard error or estimate of standard error of R head T star. And this rule actually responds to the variability through the SE standard error, and this rule produces a better subtree. So in this lecture, we have discussed how to prune a decision tree in case of overfitting. Further, we get a sequence of pruned trees. So the problem is how to select a particular pruned tree. For that purpose, if you have large data set, then you can divide it into the test set and training set, and then after training the decision tree on the basis of training set, you can select the best pruned tree on the basis of test set. If you don't have large data set, then you can go for cross validation, and using the cross validation you can select the best pruned tree. So I am going to stop here. Thank you.
Hi, my name is Gillette Sam, and I teach sociology at IIT Kanpur. Today, I'm going to tell you about the different characteristics of the movement of things around the world that are associated with globalization. We refer to these kind of movements as global flows. Now, the concept of global flows is quite important, and it's important for us to understand the different ways in which these flows might occur. Now, typically, when people talk about the movement of things from one place to another in the context of globalization, they're under the misconception that things tend to flow from abroad into the place where they are living. Uh, in a very sort of stereotypical manner, there is this idea that with globalization, much of the movement that occurs is from Western countries into non Western countries. Now, as sociologists, we know that actually global flows are multidirectional. So, which means that as much as there is a movement of flows from Western countries into non Western countries, there is an equal amount of movement of flows from one non Western country to another non Western country. And in fact, a movement of flows from non Western countries into Western countries as well. Let's take the example of food, for instance. You may be aware of a type of food which originated actually in China and then goes on to Japan, called ramen. Uh, for instance, the popular brand Top Ramen that is consumed in India is an example of ramen. Now, ramen, initially the movement is from China, which is a non Western country, to Japan, which is another non Western country. From Japan, this very popular food item travels to Western countries, such as the US, and also more recently to countries in Europe. So there you have a movement from a non-Western country to a Western country. And in fact, now we have very specific types of ramen being consumed in metropolitan centers in India as well. So there's another movement from a Western country to a non-Western country, which is India. So global flows, in that sense, are multidirectional. Uh, a second aspect of global flows is that they could be interconnected. Um, an easy way to think about this would be, if you have relatives who are traveling from um, the US or the UK or Australia, very often you'll see that people request them to carry electronic items with them. They say, "Oh, can you please get me a laptop?" or "Can you please get me the specific camera lens that I'm looking for?" So here you see that the movement of people, which is a person moving from one country to another country, is connected to the movement of technological items as well. So global flows in that sense are interconnected with each other. A third characteristic of global flows is that we could see that they happen in reverse. In fact, they're called reverse global flows. Uh, an example of a reverse global flow would be a, a style of music that you may be very well acquainted with, which is Bhangra. Now, Bhangra music is something that originated, as we know, in the state of Punjab. Now, as you know, the Punjab is also a state which has seen a lot of out migration, not only to other parts of India but also to other parts of the world. So, as people migrated to other parts of the world, they took their music with them. So, when people migrated from Punjab to the UK, for instance, uh, they hung on to the music that they were familiar with. So Bhangra moved from little villages in Punjab to the major cities where people from Punjab settled to in the UK. While in the UK, uh, over subsequent generations, this music was transformed. Uh, it was not only performed in its original version, but it was also performed with the addition of many different types of beats, which are more familiar to people in the UK. At one point in time, you see that this modified form of Bhangra comes back to India. We're talking about the 1990s, the 2000s. So here you see that that a form of music that originated in India moves out of India to the UK. It is modified a little and then comes back to become extremely popular in India again. So in some ways, this form of music is returning to where it started out, but in a slightly changed manner. We call this kind of movement as a reverse flow.